am very excited to introduce our speaker, Mubdi Rahman. He's the founder and principal of Sidrat Research. Mubdi is an astronomer with a deep background in research computing, management, and outreach. Originally hailing from Toronto, Mubdi has served as a research associate at the Dunlap Institute for Astronomy and Astrophysics and assistant research scientist at Johns Hopkins University. Mubdi is known for taking a creative approach towards scientific and research problems, using techniques from a broad background, from a breadth of fields to find unique solutions. His curiosity has pushed his diverse research background, spanning star formation to cosmology. Outside of his research, he has been a leading voice in STEM and community outreach, having led initiatives at Science Canada and Science Rendezvous. Mubdi holds a PhD in Astronomy and Astrophysics from the University of Toronto, and he also serves as the scientific editor for American Astronomical Society Journals. So everyone, can you please join me in welcoming him to the stage.
Thank you. Hopefully everyone can hear me. Wonderful, thank you. Thank you so much, Taylor, and thank you so much to the entire U of T AstroTours organization for inviting me. I'm really excited to be here. It wasn't that long ago that I was a grad student myself, and getting to hear all of the great research and all the great topics related to astronomy is always inspiring, so I'm glad that I have the opportunity to do that myself tonight. Tonight is a topic that I take personally. If it's not clear, I'm a Muslim and I'm an astronomer, so therefore I'm a Muslim astronomer. And it's something that I've found challenging because there's notions of what Muslims do, and astronomy was not one of them that we'd had growing up. But it's always one that I knew there was a heritage to. But I couldn't really figure out where. And I had the opportunity a few years back, somebody asked me to give a talk on Islamic astronomy. And so I used that opportunity. I knew a couple things about Islamic astronomy back then, but to try to do the research. And every single time I looked into a paper or a book, my world expanded. And not only was I getting excited and enthused, but I was also getting mad. And mad that I didn't know these things, mad that I didn't realize that these things were a part of our heritage. And they're all part of our common scientific heritage. So that's what I'm going to be talking to you about today, is a lot of these pieces that we've forgotten about our own scientific heritage. But really, it all starts with staring at the stars. It sounds cliche, but this is one of the things that really helps you understand how the universe works. When you take a look at the stars, you can't help but notice that they move in the sky, and there are motions that are attributed to them. We've known this since antiquity. Every human being who has had a dark sky, which was a large fraction back then than now, has been able to notice that the stars seem to move in the sky. In fact, there are some stars that move peculiarly in comparison to the rest of them. In fact, they seem to go forwards and backwards depending on the night with respect to the rest of them. They were called planets. But naturally, there's only a handful of things. If you only see these little dots of light at night and you see that they're moving, there's only a handful of things that you can do with them. And one of them is count them. But the other thing is measure how they move. What are their motions? What happens on a daily or nightly or even a yearly basis. And so that's what inspired so many astronomers up until this day, is just even without any fancy telescopes, without any modern technology, just trying to read the motions of the stars. And so how do we actually go about that? We start building observatories. And so this is something that has started from the times of the ancient Greek and the ancient Babylonians and the ancient Chinese. We tried to find ways of better observing and trying to measure the motion of stars and the positions of stars at any given time. Some of those stars are actually planets, and they were noted, and they were peculiar. But what you try to do is you try to figure out where exactly they're going to be. You try to measure exactly how they are. And imagine in a world where you have never actually seen a commercially made ruler, how do you actually try to measure very precisely the positions of these stars? So people built observatories. And these observatories are not like the observatories that you see in this day and age. They are things that basically had tools like big armillary spheres, like this thing over here, that would allow you to put a frame of reference. It allows you to figure out, every night this place is north, and I can try to figure out how far from north. I can make little inscribings to try to figure out when that star crosses from north to south, or when that star crosses certain points in the sky. And as you can imagine, the bigger you make this thing, the more accurately you can do it. So you can measure motions. The next thing you ought to try to measure is time, right? None of this matters if you can't tell the time. And anyone want to take a guess at how they used to tell time back then? The sun primarily, which is not useful in the middle of the night. So they had to come up with ingenious ways of keeping very steady, accurate time. In fact, your observations were only as good as how well you could keep time. That was surprisingly the biggest challenge back then, is getting good clocks. In fact, if you look back to Ptolemy in the Greeks, he argued that he could only have done better if he had a better clock. This is something that he literally said in Almagest, his major large book. And so the technology of developing clocks for observatories was critical to being able to measure accurately where stars were at any given point in time. The other thing that you can probably do is you can try to measure the size of things in the sky, right? Most of them look like they're about the same size, but you can try to carefully measure. The moon's bigger. The moon actually looks bigger than any star. You can probably tell with your naked eye that Jupiter looks bigger, and maybe Mars looks a little bigger than your average sort of dot of light back then. And so they would build these massive devices to go and to try to measure the size of things on the sky. And so this is what the sort of standard instrumentation of an observatory looked like back then. This is in the age pre-telescope, and all they were using were their eyes to be able to do this. But they built these things far and wide. So one of the big ones, one of the first ones in sort of the Islamic classical era was in Baghdad, the Mahmatan Observatory, which was associated with a group called the House of Knowledge. So it's a funny story because this is actually considered, often quoted, as the first state-sponsored science project and scientific institution in the world, where they had a caliph who was the ruler of that era, who was so interested in knowledge and specifically understanding the universe, that what they did is spent a large amount of money building these tools in an observatory and impressively being able to measure the positions of the stars so accurately, about 800 or 900 stars, so sufficiently accurately that they were able to, really be able to measure how fast things were moving. Further down the list, another one, and I'm only doing sort of the highlights of these observatory tours, is the Magara Observatory. This is now in modern day, what would be modern day northwestern Iran. And this is one where astronomers such as Al-Tusi, who is a name that will come up a couple times as I talk, started to do his work. And one of the things that was really interesting about using even bigger observatories, and in fact what they did is when the Mongols were sacking Baghdad, Al-Tusi took the manuscripts from Baghdad all the way over to Magara, and that's how the start of the Magara Observatory became, and how how the volumes were there, and how they knew how to build so many of the different pieces. And one of the interesting things here is this is where we get the first start of non-geocentric planetary motions. This is where they started doing the math to try to figure out, are there other frames of reference that you could set the solar system on? There's no reason for the Earth to be in the center of it. In fact, the work that was done by Al-Tusi in the 13th century was directly what affected Copernicus a couple hundred years later, right down to the Arabic letters that he put in his book to do the proof. But it's not limited to the Middle East. One of the great things about learning about this era of science is the diversity, the great diversity that occurred all throughout. So one of the big observatories, especially in the 15th century, was the Ulub Beg Observatory, which was in Samarkand, which is in modern-day Uzbekistan. And this is another sort of endowed observatory where, again, this is all pre-telescope, so you don't have the ability to, actually see, collect more information about stars, but you can try to measure their motions even more precisely. And to show you the level to which they cared about this, the observatory walls were lined with marble. Right, this is a couple centuries ago, and they decided to put marble. No observatory I've seen to this day and age is marble in it. That's not a part of our budgets here. But they cared so much about this piece of scientific, of instrumentation to try to make it something that was to be proud of. And then finally, one of the last great observatories sort of in this classical Islamic era was the Istanbul or Constantinople Observatory. Which we'll come back to again because it's also an interesting story of sort of the interaction of the state in science. So with the Istanbul Observatory, this is Taki al-Din, who was an astronomer who was the director of this observatory, was endowed by the Sultan at that point with essentially a unlimited budget, so much so that up to its maximum, at its maximum staffing, there were over 1,000 people working in this observatory. And they were trying to measure the positions of the stars. In fact, the accuracy to which they measured the positions of the stars was, if you looked at the back of the hall from where I am, it would be basically being able to measure about a centimeter in the back there from where I am, about an arc minute. That's 1/60th of a degree. And that number is interesting because that is actually about the finest our eyes can see. Right, so at that point, you didn't have any better that you could do in terms of trying to measure the positions and the motions of everything that was out there in the sky, time and time again. There's also an important story for the astronomers and the scientists in the room to not sort of go beyond what you expect. So the reason that it only lasted for 3 years is because Taki al-Din, to the Sultan of the time, made an astrological prediction of how it would be they saw a comet, and that would be a sign of good fortune for, at that point, the Ottoman Empire. Turns out it was the start of a big drought. Not so great, but what that meant is that gave a lot of the critics of the observatory and all of this a lot of ammo to try to close it. And that's one of the reasons why you don't actually see the great Istanbul Constantinople Observatory still standing anymore. But one of the things that happens when you get really good at looking at the stars is you start to learn a lot more about the light that's coming from them. And not just the light that's coming from them, light in general. So one of the prominent astronomers of the time, Al-Haytham, studied light in the service of trying to study astronomy and trying to understand this. In fact, often considered one of the founders of modern optics. And it's impressive, even without the scientific instrumentation that we have today, what you can figure out about light. So one of the popular ideas back then, coming primarily from the Greeks, was that the way that you actually see things is that your eyes spit out some sort of ray, and it samples that, and that's what you get. It sounds laughable today, but if you don't have a reason to believe that's not the case, right? Like, I close my eyes, the rays go away, open them, and they're back then. One of the things that Al-Haytham reasoned was that couldn't be the case, that the light had to be coming from things from the objects themselves. Another thing that he reasoned, which again is something that was was considered commonplace once it was thought through, but was a bit of a revolutionary thought there, was that the light had speed. That the light couldn't just be at every place at every time, that it had some speed. He didn't know what the speed was. He assumed that it was so fast that he couldn't measure it, but that it wasn't instantaneous. That light didn't travel instantaneously. But then it gets really, really cool, because when you start with those basis, or things that you want to experiment on those bases, you can start measuring properties of light based on the stars and things that you're seeing. And one of the things that you can see every day is the sun going up and the sun coming down. Well, every day that's not cloudy. Even astronomers back then had to deal with weather. But what he was able to do is measure, and I shouldn't say just he, because he was in concert with a large number of astronomers and scientists at the time who were doing the measurements, but was able to measure the time that they expected the sun to rise and the sun to set. And interestingly, the sun seemed to rise earlier and set later than if you just measured the time it took for the sun to move. Based on that, which is something we still see today, how many of you have seen a sunset on the beach? How many of you have seen the sunset after the stated time of sunset? Or seen the sun after the stated time of sunset? If you look at your watch and carefully pay attention to the time, and when you still see the sun, you'll find that the sun still appears on the sky after sunset. And that is because the atmosphere is refracting the sun, so you're actually seeing the sun below the horizon. And it's coming through the atmosphere. And so you're actually seeing it below that time. And this is one of the things that was thought about before, but it actually was able to measure. And that then brings on another real piece of interesting, reasoning, which is if you start studying refraction and you know that light seems to have some speed, and you know that when light bends, it's because it's going through different materials. You can see that through water, for instance. It's not particularly surprising. He reasoned that space, whatever was outside of between here and the sun, had to be a lot less dense. There had to be a lot less stuff there. In fact, it had to be basically empty in comparison to the air. Because you could essentially measure that angle that you can see the sun further below. And so just from seeing the peculiarities of light, you can start to piece together a lot about how light in general works. But here's a really cool one that actually has it's a bit of an aside, but has not much to do with physical light. You've probably seen this. How many people have taken a look at the moon at the horizon and seen that it looks massive, but then gone up and looked at the moon in the middle of the sky and it looks tiny? Right? How many of you have tried to take a cell phone shot and saw that the moon looks like nothing on your screen other than like a bright dot? So this is something that's been known for a while, but it's called the moon illusion, and he talks a lot about that. And one of the things that you can do when you have the tools to measure the size of things on the sky is that you can actually measure how big it is on the horizon versus how big it is on, when it's higher up, and you can see that they're basically the same. And so what he was able to establish that was then, talked about by Francis Bacon and other, physicists, in the times later, is that this was basically a psychological illusion, that the frame of reference that we have on the horizon is making it look bigger. But when we lose that frame of reference, we just don't have the ability to essentially place what size something is. So all well and good. But another thing that you can do when you start playing with the nuances of where things are in the sky and where, and how light works, is you can want to try to figure out how far things are. And so a very simple process of trying to figure out how far things are is something that your eyes do all the time, right? It's the idea of if you step to the left, everything moves in respect to what you're looking at. And if you move to the right, everything moves again, right? But the things that are further seem to move less, and the things that are closer seem to move more. So this is a concept called parallax. It's one of the simplest concepts, but it's a very powerful one, because it basically says, just based on the angle that I see things, based on the angles that I see things, I can tell what the distance of that thing is, right? Because I know how much I moved, and I know what the angle is, so therefore I should be able to tell how far that thing is. And so at the time of the Greeks, they had measured this already for the sun, and they'd already measured this for the moon, right? They're close enough, they're big enough that you can start to do this. And those measurements started to get refined more and more. But at the time of the great sort of classical Islamic observatories, they tried to measure this for stars. Most stars are actually pretty far away. So what they had determined from this is that it had to be further than a certain distance because they couldn't see it. And they also didn't realize quite what the Earth was doing. We kind of do now, because what really wins and what helps you when measuring parallax is how far away you're looking. If I'm over here versus if I step over here, the angle is a certain distance, but if I go double the length, that angle is twice the amount. So the further I move, the bigger the angle is, the easier it is to measure. We've got a really far distance that we travel on the Earth. For instance, let's say that we're taking a look at the star up at the top right. And so we measure the angle there. And then we wait 6 months later. And so the Earth travels around the sun. And then we measure the angle over there. That then gives us a measurement of how far those stars are. The challenge is it's actually really hard to do. In fact, the first time this was done was in the, I believe, 1800s with a telescope, because even the closest stars that you see, the amount of motion that you expect, or the amount of motion that you see, is no more than 1/3600th of a degree. Right? Remember that the smallest our eyes can separate without a telescope is about 1/60th of a degree. So these were tiny amounts, and really gives you a sense of just how large these distances are. But in this day and age, we have other ways of doing it. One of the ways that has been really impressive and prominent right now has been the Gaia satellite, which is dedicated to just going and measuring the location and measuring the motions and distances of all of these stars. And one of the areas that it tries to look for is it tries to look in the Milky Way. So we're going to take a little bit of a recourse on the Milky Way, because this is something that we've also seen since antiquity. You can go out to a dark place and you can see the Milky Way. Right? It's a fantastic, beautiful thing. If you haven't had a chance to get beyond the lights of Toronto, please do. It is incredible to see for the first time. I'm a city boy. I didn't see it until I was in my 20s. And let me tell you, it did feel life-changing at that point to me. But back in the day, without really much artificial light, you saw it all the time. And so it wasn't that big of a deal. But there were lots of discussions of what this might actually be. But now when you start to understand light and understand the measurements, you could try to actually figure out what it might be. And so in fact, Hal Haytham, that person who studied light, actually attempted to do the parallax of the Milky Way, tried to measure how far this thing was. And the one thing that he was able to reason is that it wasn't a part of the Earth. That's about all that he was able to do, because it's really, really far away. But they had large, endless debates about this. So for instance, Al-Biruni, who was based sort of in, I believe, sort of Southeast Asia, or South Asia at that point in time, speaks in his book that the Milky Way is a collection of countless fragments of stars. Right? That's what the presumption was, because they saw that stars had different brightnesses, and the assumption is if there are more stars, there's going to be a point where they just look like big balls of gas. And this is further talked about by Al-Tusi, who says that the Milky Way is a galaxy made up of very large numbers of small, tightly clustered stars, which, when accounts for their concentrations and smallness, seem to be cloudy patches. So not quite the modern, these stars aren't small inherently, but it gives you a sort of a sense of the kind of argumentation and kind of exploration they were trying to do to try to figure out what they were looking at and what the physical origin of it was. But with Gaia, not only can we figure out what the physical origin of it is, we can see individual stars, and we can actually measure their motions. This is a movie of the measurement. In fact, let's restart that. of, sorry. Apologies. But you can see that there is the physical motion of these stars that has been measured. In this picture, there are over 1 million stars that they are measuring over time the distances of. Not only the distances of, but their motions. But you can do more than that. You can even look at groups of stars that seem to be moving together, and you can say that these may have come from the same place and moved in the same place. And be it from galaxies that our Milky Way has eaten up, or be it from star clusters that had traveled through the disk and slowly expanded. But we're able to do that now. And we can even then look at the disk as a whole. And so one of the big discoveries that Gaia has made is looking at essentially the warp of the Milky Way and being able to measure how much that changes and how much that will change over time. And all of this because we're just looking at a bunch of stars. Something else that Gaia saw is this thing. Anyone want to take a guess at what it is? Yep. It is Andromeda. It is a galaxy. In fact, it is our closest neighbor galaxy. And so this is basically one of the challenges of being within the Milky Way is that we don't see ourselves as a full thing. We can only see within it. And so that makes it hard to understand what we're actually doing and what our galaxy looks like. But we're actually very lucky because we have a galaxy that's very similar to us, not that far away. In fact, it's getting closer every day, and eventually in a couple billion years, it's going to be a part of the Milky Way. But for now, it's a little further away. And we can actually try to figure out what that galaxy is doing and how it relates to what our galaxy is like. But this is where we get to go a little bit back in time to the first mention of the Andromeda Galaxy that we can have known is, is in Al-Sufi's book of fixed stars. So one of the nice things about the Andromeda Galaxy is that it's faint, but you can actually see it if you're in a dark location with your own eyes. And so it appears that the first time that we've seen mention of it or observed, any indication of it observed in print is that little red speck over there with the note saying that basically this doesn't look like any of the other stars that we saw. But this is probably a good time to maybe stop and talk a little bit about how we organize science. Because all of these things that I'm talking about, they're interesting sort of one-off discoveries, but part of it is that they've kind of gone through a process of people who are trying to look for one thing and found something else. But what we talk about science in terms of in modern day, we think of it as very monolithic often. Right? Science is a thing. It's separate from the arts, it's separate from humanities. It is its own thing. It's its type of knowledge that we try to get. And that we can break that down further in terms of life sciences and physical sciences. So science is related to things related to us, and science is related to things about the physical world around us. And we can break that down even further into things like biology and zoology, and astronomy is one of them. If there are any physicists in the room, I'm going to keep astronomy separate. I don't care. Astronomy is its own thing. But there's no reason, the universe doesn't care about our distinctions, right? In many cases, the purpose of these distinctions is to try to make our lives easier, is to help us try to organize knowledge. And it doesn't have to be this way. These can be very arbitrary. The only thing that's useful is if they help us try to understand the world and the universe around it. And so what that means is that there could be many different ways of organizing knowledge. In fact, there have been. So in much of the classical astronomy, or classical Islamic astronomy times, a lot of what we talk about in terms of astronomical knowledge comes from one branch of Islamic astronomy called Ilm al-Nujum, meaning knowledge of the stars. And what this really is the way that they had organized knowledge at that point was that this was actually a part of math. It was considered math to be studying the positions of the stars. which is not crazy. Does anyone happen to know what we used to call astronomy and science prior to calling it a science in the Western world? Anyone want to take a guess?
The quadrivium.
Pardon?
Quadrivium.
A little after that, oh yeah. There's a reason that I have a doctorate of philosophy. We used to call science natural philosophy, right? Because that's one of the ways that we organized knowledge back then. But in Islamic science, they organized knowledge into sort of more mathematical and calculation based, and so the measurement of stars was considered mathematics. On the other hand, there was something called ilm al-haya, and this is something that often gets missed by a lot of especially Western commentators. And this was essentially the knowledge of the creation, or the knowledge of the structure of creation. And within ilm al-haya, you had physics, you had metaphysics. It's sort of this interesting blend of how does the universe exist as a whole. So you had a lot of what we'd now call theoretical astronomy. You'd have a lot of what we called cosmology back then. And yes, you'd have a lot of what we called astrology in that same kind of, category. And this is the stuff that we've often thrown away in our Western historical view of Islamic science as saying it's garbage, but in reality, this is where the interesting thought went. And this is where you saw interesting discourses between astronomy and theology, and astronomy and physics, and astronomy and legal traditions even. All of these things happened through ilm al-haya. And so we're just starting to rediscover it in the Western academic tradition, that all of these things were happening. And how was this communicated? So one of the key pieces of how information was communicated was in these things called zijs. I can barely pronounce it, I apologize. But it comes from the Persian term for cord. And because they are basically tables of the positions and accurate depictions of where all of the positions of the stars that you saw and the planets were at any given time. In fact, the accuracy of these were so high that in looking at them, you could actually measure the precession or the wobbling of the Earth's motion over time. In fact, more than just the tables of numbers, which a lot of this is, a classical Arabic table of numbers, the astronomers will be amused to note that there are 3 columns here. Any astronomer or an amateur astronomer want to guess why there are 3 columns? Pardon? They're coordinates, but why are they 3 specifically? And every single astronomer has probably been really annoyed by this in the past, because we all like decimals. Yep?
What is time?
So it's all time related, but I think I heard something over here. It is right ascension declination, but it's specifically in the system of hours, minutes, and seconds, which everyone who has tried to figure out where something is in the sky has been, annoyed by at some point in time, because the hours we measure in right ascension are different from the degree or the hours we mention in other things. So, but blame the Arab astronomers and the Islamic astronomers for that if you want to. But what they would also do is they'd encapsulate a lot of knowledge of the methods that they use to calculate this. They'd encapsulate a lot of knowledge and writing about sort of the techniques and what they thought this was telling them and how these were different. And in fact, one of the things that was very common to do is, in this tradition of astronomy, in this tradition of science, there was this sort of reverence of the people that came before you. So oftentimes, what they would do is actually in translations, they would, in the margins, and you can see this in translations of especially Ptolemy's work, in the margins, they would actually just accidentally correct positions and attribute them to Ptolemy. And say, oh, he just made a simple mistake or a translational mistake or something, and it was him. In fact, much of the precession, much of the discovery of precession was masked by this process, because we didn't realize that star was actually moving in the sky, when in reality it was, because he didn't make a mistake. It was just actually different measurements of the star over time. But these things traveled, and these things would be collected everywhere. Every observatory had them, and they were collected from different times, and you'd have them in your libraries. In fact, so much so that we essentially do this to this very day, right? What we call jizzes are basically proto what we now call ephemeres, basically the position of all of the sort of planetary bodies and all of the major stars in the sky. This is something that this is still a part of the exact same tradition. So if you go to Jet Propulsion Laboratories, in fact, you don't even need to go there, you need to go to their website. What they do is they actually calculate the exact precise position of all of these objects. So you can put in a time, a date, and an object, and it'll tell you often down to a centimeter how far that thing is and where exactly that thing is. And this is all in the exact same tradition. But one of the things that comes from looking at this is recognizing that astronomy is a team sport. Science has always been a team sport. We have this romantic notion of astronomers or scientists sitting, locked away alone in some, romantic or, antisocial corner of a castle somewhere and trying to, peer over their books. But nothing has ever been further from the case. Astronomers debated, scientists interacted, they argued with one another. All the way from the 8th century onward, there were dramatic brawls between different people who were trying to figure out what was going on in each of these cases. One of these places that this happened was in Timbuktu. And so one of the places, so you may have heard Timbuktu in the sense of, it's a faraway place, and that's often where it's, what's used in Western literature, of this crazy distant place that there may be riches. But what Timbuktu is basically a large center of learning. And people would travel across continents to get to Timbuktu, right, to see, this is the Sankwara Mosque and university, and it's at its height, over 25,000 students would come here to learn from all across different continents, to learn from teachers and to learn from all of these different books. And the manuscripts are only now being started to be translated. And we're only now starting to see this sort of interaction and interplay of scientific knowledge through all different fields. But beyond that, we also have different tools of the trade. And that's one of the ways that we know that, that astronomical knowledge was propagated. One of the big ones was the Astrolabe, which is something that, when you talk about Islamic astronomy, we often talk about. One of the ones that I want to point out that's really interesting is the celestial globe tradition, because this is one that really highlights the interaction of Islamic and Hindu astronomy, where there was a family that was actually in Lahore, in modern-day Lahore, that from the 12th century onward, they were the only ones to be able to produce these seamless brass globes. And you could see that they incorporated different coordinate traditions and different positions of the stars based on their different times. And they would have Arabic and Sanskrit, and all of these were often ordered by various wealthy merchants and various wealthy rulers at different times, sort of combining both the Arabic and the Hindu astronomical traditions, all sort of at once. Because there wasn't a separation, and they didn't see a separation. There wasn't a Hindu astronomy, and there wasn't an Islamic astronomy. There was just astronomy, and they were all trying to figure out what the world looked like, what the universe was like. And this happened, this isn't just a one-place thing. This happened all over the world. For instance, in the Song dynasty, in my years, was a Hui Chinese Muslim astronomer who was the astronomer of court that helped integrate a lot of Chinese and Islamic astronomy traditions. In Timbuktu, we already talked about that, but there's a lot that happened in sub-Saharan Africa, especially with classical African Islamic astronomy traditions. In Kashmir and Punjab, we had Al-Biruni, who was one of the people who was able to piece together why we should be talking about these things as empirical, and why we shouldn't be throwing things out just because they weren't, he was a Muslim astronomer, but he wasn't throwing out Hindu works. And one of the things that he actually wrote down is to the people who say that we shouldn't follow the Hindu works at that point in time, the Hindus eat food as well, should we stop eating food? Literally written down. It's kind of, In Jaipur, here's another wonderful place where the Hindu leader of Jaipur, Maharaja Jai Singh, who the city was named after, actually commissioned 5 observatories to be built to measure this in the 17th century, I believe. So remember, this was happening at the same time as the British India Company was essentially, parading and colonizing much of the rest of India. But then we also have the European centers. Toledo, I haven't even really talked about, Islamic Andalus. And Toledo was this big center where Jewish, Christian, and Muslim astronomers and thinkers and logicians and astronomers would actually translate works. And there were great libraries in there that had all of these well before the Spanish Inquisition sort of set a lot of these things aburn or sent them on their way. We have Montpellier, which was a great place in France where people were commissioned to go out into the eastern lands, as they called them, to bring back books and translate them and make them a part of the European and Western canon. And then the School of Siena is another really big one. And this is an important one because this is where oftentimes a lot of great manuscripts would make it there. And that's where often Galileo had a lot of access. And that's where it's believed that Copernicus had access to a lot of these texts. Interestingly enough, if any astronomer ever gives you heck for trying to buy the name of a star, just let them know that Galileo tried to sell the names of stars to Medicis. So it's deeply rooted in our tradition. So I'm going to ask a simple question. Why don't we know about these things, right? This is an incredible history. This is an incredible part of our history that we don't know. And then I'm posing to you that part of it is because, especially in the 15th century onward, there was an active attempt to try to make Europe and European centers seem prominent. And so Adam Smith, any economists in the room? It's that Adam Smith, the Wealth of Nations Adam Smith, who knew nothing about astronomy, let alone Arabic or Persian or fair. Basically saying too much of those Greek systems, basically the Arabs were too tied in the wool, Greek, to think beyond that. Picot, in 1828, this is one of those things that feels like it belongs on Fox News or Rebel Media right now, talking about how, the first rude and illiterate, despising every book except for the Quran, and I hate that spelling of it, but, they would, use their irresistible enthusiasm and fanatic zeal, right? This is the kind of language that was commonplace. Lockyer, this is one of the nicer mentions. During the Dark Ages, astronomy was cultivated chiefly by the Arabians, not even mentioning the fact that half the astronomers that I talked about weren't even Arab astronomers. Made diligent observations, but they didn't really do much in terms of theory. They didn't really think much about, how the universe was constructed or anything. Bryant, this is I believe a college-level textbook from the 1907s, where they're trying to be sort of, nice about it, but like other Oriental nations, they failed in the direction of speculative philosophy and devoted their analysis rather to astrology than astronomy. Chamberlain, 1911, this whole Arabian science and philosophy was nothing but a wretched translation of Hellenic thought and knowledge. Dreyer, through Europe, a debt of gratitude is, to the Arabs, but they left astronomy pretty much as they found it, right? That is sort of a millennia of work done on astronomy, but we left it, as we found it. The guy at ESOL, website last night, basically the Arabs just, translated Greeks. But if there's one thing I hope that I've been able to convey, it's that our scientific tradition really does come from people that span faiths, continents, and cultures. And it's about time that we reclaim this heritage. I'm not sufficiently naive to believe that understanding the roots of our heritage, our scientific heritage, as coming from a large number of places, will necessarily lead to us living in a better world and living in a place that we understand each other more. I think there's a lot that's going on. There's a lot of bad that's going on. But one of the things I want you to remember is that before people were fleeing these places that we see in the news today, before Mali was overrun with guns and weapons, people would do everything they can, travel by foot to Timbuktu, that accepted anyone to try to learn from them. People would go to Kabul to do astronomical research and try to better understand the universe. We moved people and places, and I would be remiss if I didn't mention that we are in the midst of the greatest refugee crisis since World War II. These people opened their doors for us. These people and their traditions were a part of why we know so much about the universe today, and they need our help. So if you have the opportunity to, I'd strongly recommend supporting organizations like the UNHCR, UN High Council for Refugees. But I want to leave you with the Quranic verse that I actually put at the beginning of my PhD thesis because it inspired me, and I can only imagine, I have no proof to back it up, but I can only imagine that many astronomers also found it to be inspiring in the past. And it is God who placed for you the stars that you may be guided by them through the darkness of land and sea. We have detailed the signs for a people who know. Thank you very much.
Thank you so much for a wonderful talk, Mubdi. We have a couple of minutes for some questions. If anyone would like to ask one, Sam, and you should be able to bring over a microphone. So please just put your hand up.
What kind of observations do you think were lost during the sacking of Baghdad while in the Roman Empire? Like, you know, like the libraries were destroyed and all scholars lost. So what types of observations do you think they happened?
So one of the funny things that's actually, like, I grew up in thinking that the sacking of Baghdad was this great loss of literature. One of the things I've been learning is it wasn't. Not because there wasn't like great death and great sacking and burning of things, but it's because in so many cases these works had already been transmitted to other places, right? When I talk about Samarkand and the Uzbek observatories, they had libraries that basically rivaled Baghdad, right? So in most of these places, in the Samarkand instance, it was only rediscovered by Russia in 1907. Right, that there's this trove of hundreds of thousands of manuscripts that haven't been touched, that have been translated into Turkic languages and Arabic languages, that are just ready for us to go translate and understand and better understand the world. So yes, while the sacking of Baghdad may have been really destructive in that particular location, a lot of this stuff was already transmitted and it's ready for us to go find.
In your slide showing the observatory in Istanbul, they had quite a showcase of scientific instrumentation.
Yes.
I'm wondering if you could pop that up.
Oh, sure. Yeah, happy to.
And perhaps describe some of those instruments.
So yeah, this is actually the same graphic that was used for the purpose of advertising this talk, and it's a fantastic one. But one of the things right off the bat that you'll see there is, first off, the Astrolabe. So this was basically considered, people have talked about it as being the most important calculating device for astronomers until the modern personal computer, essentially. And so what the Astrolabe does is allows you to both measure where you are, the position of fixed stars that you can orient yourself to, the times that they're supposed to rise and set, so that you can actually, in the middle of the night, just completely figure out what time you are. Right? It's basically an astronomical slide rule is a way of thinking about it. And these were built, the bigger you are, the more accurate you could be. So observatory-sized ones were huge, whereas they had pocket ones, right? There's ones that you could just put in your pocket and they'd be made of brass, and you can see them. And oftentimes they're actually, they're displayed in things like the British Museum and the Smithsonian. But the big ones were actually built in, in these observatories so that you could actually have them make more precise calculations. So this was essentially an early, I believe, quadrant. And so the idea behind the quadrant is that it allows you to sort of measure relative positions of other stars with respect to the star that you're pointing at. So you have a fixed angle and you have line demarcations. And so what you can do is you can point it up and you can see, hey, that star is over there. What demarcation is that other star next to you? Because you know the angle that you've created. And so therefore you know what angle it should be away. You can move it in these different areas. They sadly don't have an armillary sphere in that. This, I'm sure some of you guys can probably guess. It's, every yacht probably has one on display now, but it's a classical astronomical sextant. Right, so this is one of the ways that you can try to measure how accurate, or what the position of a star is above or below the horizon, so the altitude. Because it's really hard to do without a point of reference. And what better reference is there than down due to gravity? This is just a globe. And this, I believe, is another set of quadrants. They surprisingly don't, they don't have armillary. There's a couple of other pieces of instrumentation that were super common. In fact, one of the things that was actually a really interesting rivalry is Taqi al-Din, whose observatory this is referring to, and Tycho Brahe's Uraniborg were actually contemporaries and were rivaling each other for the construction of the best astronomical instruments of the time. So they copied each other. There was a lot of intellectual theft going on there between those two places. Hopefully that answers some of your questions.
First of all, thank you so much for an incredible talk.
Thank you.
It's been very much focused on the past, and if I can bring it to the present day, you mentioned at the start of your talk that growing up as a Muslim, you didn't see astronomy or astrophysics as something that you would necessarily do. Why is that? And more to the point, what do you think you can do to change that?
So let me rephrase that. I always thought I would do it. My parents didn't think I'd do it and actively tried to work against it. And I understand, they're immigrants from Canada, they grew up poor, and the thought of their kid being a starving astronomer was not one that they cared to do. But there's also just this notion of, I think within, and I'm gonna speak primarily from my experience, so please don't no one take offense to this, I apologize. But within some Islamic communities that I have been a part of, there's this notion of very common paths that one is supposed to take. And I think there's a lot of folk wisdom to that, right? You understand that you want to create, you want your children to be successful. I'm a little choked up because we're actually, my wife and I are expecting in December. And so just thinking about what we're going to tell thank you. But I think the biggest thing is sort of recognizing that there are more paths than we can fathom as human beings. And we don't know how we're going to make an impact. We don't know how we're better going to help other human beings or how we're going to better understand, in my belief, creation. And I think that openness is so critical because that's what allows us to better understand the universe as a whole and to get to places that we never thought we could. And that's what I think we need to be open to.